Okay. If you haven't answered the poll, give it a click. We'll close it out in about 5 seconds. Okay. Share results. So, according to our informal sampling of the people here, yes, we have 25% double E, 69% copy, and then 6% another type of engineering. So welcome to our two friends that are neither double E's nor copies. We're glad you decided to take the course this summer. And then I guess I need to steer myself towards compy discussions during this course. So there was no right answer to this quiz. Good news. So, all right. Relaunch download results. Cool. I'll just yoink that into my course files. All right, sharing the screen now. So last time we went over the syllabus and then we started our discussion about the operational amplifier. But since we want to be on good speaking terms with the op amp, we are going to call it the op amp. The goal is that the idea is that it takes in, one or more input voltages and produces a linear related output voltage. Linear as in linear differential equation. So we'll see today that it can do derivatives and integrals and things of that nature. And it can do all these sorts of different mathematical operations. And mathematical operations is the reason for the name operational amplifier. That's why it was constructed. It was to be part of analog computers. So we talked about the symbol where it's got this inverting input with the minus sign, the non-inverting input with the plus sign, and then the pointy end of the triangle is our output. And then we can have,
Michael,
yes?
excuse me, I don't think you're sharing the slides. You're sharing something else.
Ah, I will stop sharing. I just click the button, entire screen, screen one. Can you see the slides now?
Yes, indeed. Thank you.
Cool. No, thank you, Siraj. Uh, that was embarrassing, but that's okay. We press on because we're engineers and we don't let one little mistake get us down. We let a plethora of mistakes get us down. And we're going to use reference designator U for our op amps in this course. Cool. So the ideal op amp conditions, again, this is something I would star, is, we're going to say that there are 5 of them in this class when in reality there's like 11 or 12 of them. So ideal differential or infinite differential gain, infinite input resistance, 0 output resistance, infinite bandwidth, 0 DC offset. And then when we analyze a circuit, we're going to create a virtual short condition that puts the inverting and non-inverting inputs at the same potential. We'll say there's 0 current drawn into the device, which seems like a contradiction, but don't worry, it's part of our analysis. And the output current can be whatever it needs to be. So we looked at this differential amplifier configuration that takes inputs V1, V2, and then produces an output voltage between V3 and V4. We went through the math. We noted that all useful op amp configurations have a feedback path. And then we got this expression where RF over RN serves as the gain of the op amp. And it doesn't depend on any of the sort of internals of the op amp. There's no, U1 related terms in there. So we're not going to get any sort of distortion from the nonlinearities there. And then at the end of last lecture, I said, our goal is not to memorize amplifier configurations, but to be able to derive the output voltage equation quickly. However, that's kind of a cop-out teaching if we don't look at any of these configurations. So I'm going to sort of contradict myself by actually showing you a whole bunch of amplifier configurations. But again, the idea is not to memorize all these sorts of V-out equations. Conversion time, despite being an analog type of circuit engineer, I don't have most of these configurations memorized. I just rederive them on the fly. So take that for what you will. So the first new slide of today, the 14th of June, is the inverting amplifier. And this one's probably worth spending some time studying. So some remarks on this configuration: the input goes through a resistance Rn to the inverting input of the op amp. The non-inverting input is tied to ground, and then there is this resistance Rf in the negative feedback path. So if we analyze by KCL, we'll say that Vn minus Va over Rn plus Vout minus Va over Rf must equal 0, because the currents going into node A must sum to 0. However, we can immediately make a substitution that Va is equal to 0, ground, because of the virtual short condition. So we end up with this equation on the screen here. And then this should be a lot of straightforward algebra to just say Vout is equal to negative Rf over Rn times Vn. Or if we write it as a gain, Av is equal to negative Rf over Rn. And if you do a little bit of massaging to the differential amplifier, where you basically let the lower RF feed forward resistance go to 0, or excuse me, go to 0, and you let Rn also go to 0 and neglect the input. Like, there's a whole bunch of changes you'd have to make. You could get this. However, I think it's easiest just to rederive it rather than treat it as a special case. All right, let me check comments. What is meant by I out can be what it needs to be. Basically, what I'm trying to say is when you're solving for conditions, don't try to write a node equation for the output. One that's sort of usually treated as a, I guess, quote unquote, known potential or a potential you're solving for. But if you try to write an equation here where you're trying to figure out the current coming out of the op amp, you won't be able to determine it. Therefore, you're not going to get a very useful KCL equation there. In general, we focus on ideal or non-ideal op amps. Ideal. This is a linear circuits class at heart, and the op amp's only really linear and ideal. We will talk about some of the non-idealities when we get to chapter 7 material, which is at the end of this lecture. How do we get negative Rf over Rn? The node occurrence will be in opposing directions. That answers why it's negative. Is there anything more specific I can explain for you, Appersaw? I don't actually know your name. Do you assume that Vout has a higher potential than Va? I'm just assuming that the current is going into Va. So I will say that Vin minus Va over Rn is the current going into A from the Vn side, and then Vout minus Va over Rf is the current coming in to Va from the Vout side. Notice that if you were to choose your resistances carefully, say you make RF smaller than Rn, you can end up with a instead of an inverting amplifier, it becomes an inverting attenuator. So you can end up with gains that are less than 1, or I guess in absolute value are less than 1, which means attenuation. Oh gosh, so many comments. Let me make my chat section a little bigger. Yes, I was using RF, not R out. Why again is node A at 0 volts? Because of the virtual short condition. If non-inverting side is a voltage choice with the current through, no, it would be whatever the potential is at this place. So if there was a voltage choice here of say 1 volt, then Va would be 1 volt, and this equation wouldn't work out the way it did. All very good questions. Any more?
I have a question. Is there a reason we use the virtual chart? Is it useful, or is it just something we do because it makes calculations easier?
It's useful. It's real. In the sense that, as much as any amplifier is ideal. So
Mm-hmm.
we say that we have a virtual short causing the terminals to be the same potential because every configuration we study has a negative feedback path. So the reason is basically, if this truly has infinite gain, then any difference between these terminals would produce an infinite voltage output. So we're going to say that the op amp is going to do everything in its power to make these two potentials the same. So in order to make these potentials the same, that means there would be zero potential difference, which means, you can have a, 0 times infinity is an indefinite form. So that allows you to have a finite output voltage.
Mm-hmm.
Did that explain your question, Suraj?
Yes.
Or answer your question?
Thank you.
You're welcome. What does a virtual short look like in application? It looks basically like this, where we have this negative feedback path, which allows for the virtual short condition to be true. If we don't have negative feedback, we have what's called a comparator, which is a special form of op amp, where it literally just tells you which side is bigger. Which, yeah, I guess we don't talk about comparators. I should write that down as a missing part of the curriculum. Any other questions? Hearing none, let's go ahead and move on. So we have the non-inverting amplifier, another configuration I recommend you study. So now we have the input goes into the non-inverting input, so the input voltage. The inverting input is tied to ground through resistance Rn. So we have this resistance that goes between ground and the inverting input, and then the negative feedback path has resistance Rf. If we're to do the KCL in virtual short condition again, I always like to sum currents in. So I say 0 minus VA over Rn plus V out minus VA over Rf equals 0. However, by virtual short condition, we have a voltage here, not ground. So we say VA is equal to V in. So with the one KCL equation and the virtual short condition, we can solve this and get that V out over V in with a little bit more cleverness of our algebra is 1 plus RF over Rn. So notice there's no minus sign. That's why it's called a non-inverting amplifier. The sort of downside is instead of being purely, a ratiometric type of thing where it just depends on the ratio of resistances, there's this factor of 1 floating in there that gets added. Okay, sorry. I'm a little paranoid that I'm going to miss a question. Speak up if I do miss a question, like use your voice, project. Okay, so now what happens if we look at a limit of this expression? We're going to look at the limit of this as RF goes to 0 and Rn goes towards infinity. So Rn gets replaced with an open circuit, RF gets replaced with a short circuit. We get what's called the voltage buffer, which is something I imagine you saw in ECE 2007. You'll definitely see it in ECE or 2008 lab. But, again, it's here, negative feedback path, inverting input is left open with respect to ground, and, we have the input here. All this does is produce a voltage gain of 1. Why is that useful? You're like, what good is a gain of 1? Well, it allows you to have things like a resistor divider on one side and take the output voltage across and feed it into another resistance without loading the original voltage divider. Because otherwise, if you put a resistor in parallel with one of the resistors and voltage divider, you have fundamentally changed the topology of the circuit, and that changes the amount of current being drawn through the resistor divider branch. So it allows you to connect various parts of your circuit together, get the voltage without changing the current relationships in each of the stages. Question. Nope. Okay. So next configuration we're going to look at is the summing amplifier. So we have inputs, V in 1, V in 2, V in 3. You can extend this, to V in K, where K is just some integer. And then resistances R in 1, R in 2, R in 3, up to some R in K. And then non-inverting input tied to ground. And then this is a resistance RF in the negative feedback path. Do all of the same math again. You get V out as negative RF, and then the scaled sum of your input voltages. So this is just a modification of the inverting amplifier to take more inputs in. And suddenly we're able to do addition with signals. This is kind of a big deal. Now we can take, for example, like a square wave and then a sine wave and add them together and get an output there. So you can imagine where, like, say if you played like electric guitar, this might be a very useful way to get more effects in your effects pedal or something like that. Or if you're just trying to, do analog computation, or just, anything that requires, something as basic as addition, you're able to do that with a summing amplifier. The integrating amplifier is just another configuration. Here we're not going to use a resistance in the feedback path. We're going to use a capacitance. So it looks very similar to the inverting amplifier. And then if we remember the capacitor constitutive equation, or remember that for a capacitor, we have that the current through a capacitor, IC, is equal to C times the derivative with respect to time of the voltage across the capacitor. So we're going to get for KCL Vn minus 0, because VA is equal to 0 by virtual short, over Rn, plus the current going through the capacitor, which is CF times the derivative with respect to time of V out minus 0 equals 0. Solve for V out, and you get, this sort of inverting integration where it's negative 1 over Rn CF, integral from tau equals 0 to t of Vn of tau d tau, plus whatever the voltage was at time equals 0. The other way of writing it is on the bottom left, where it's just written as a derivative. Well, if you know anything about electrical engineering, you know that we like to present one thing and then present, something that does the exact opposite immediately afterwards, and I'm going to be no different. So the opposite of integration, the dual operation, is differentiation. So if we swap the positions of the capacitor and resistor, we're going to get an output voltage of negative RFC and dV and dt. Again, the goal is not to memorize these things, but the goal is to sort of recognize these sorts of patterns and be able to derive their output voltage relationships on the fly. Any questions? This ties up the first section, the first topic on ideal op amps. Hearing no questions, we'll go ahead and press on. So I have some notes here. So why study transistors? So we're going to talk about MOSFETs now. And this should be largely review of ECE 20001 material. However, not everyone is instructed the same way. So we're going to do a crash course. We're going to present a lot of slides in a short amount of time to review this material. So why study transistors? Well, transistors are three-terminal devices, and three-terminal devices are useful because they can act as transconductance amplifiers, current sources, and switches. Basically, the heart of digital circuits today is the ability to control the current through one terminal of a device by a voltage between the other two. So we have, two terminals that serve to take a voltage control, and then the result of the control is a driving current through the third terminal. So we are specifically going to study the metal-oxide-semiconductor field effect transistor, MOSFET for short, because it is a, in scare quotes, simpler transistor than its cousin, the BJT, or bipolar junction transistor, because the MOSFET passes zero current through its control terminal, whereas the BJT requires some control current. We have cut BJTs largely out of the curriculum for double E's and comp E's. So we are going to talk exclusively about MOSFETs. BJTs will be reserved for future courses should you decide to pursue them, like ECE 305 or 455. MOSFETs have a high input impedance and low power consumption, making them ideal for digital designs. Hopefully that causes all of the compies to perk up when I say the word digital. That's kind of the Pavlovian response I'm going for. So the vast majority of transistors in the world are MOSFETs. Like if you were to survey all the transistors in the world, like 95%, if not 99.5% of them would be MOSFETs. They're first patented in 1925. It took until 1960 to actually build them at Bell Laboratories, and they've been dominant since the 1970s. So the inventors of the MOSFET were Dawan Kang and Mohammed M. Atalla. Mohammed M. Atalla being noteworthy because he was a Purdue graduate. He got his MS in mechanical engineering in 1947 and his PhD in 1949. So believe it or not, mechanical engineers were instrumental in making the MOSFET because actually fabricating the darn thing was the hard part. Miniaturization, straightforward manufacturing processes, and the ability to avoid many resistors and capacitors and decides have led to a VLSI explosion. VLSI is very large scale integration, the ability to pack over 1 billion transistors into a given area. And, we call this sort of exponential growth of the number of transistors in a given area Moore's law. Most small signal discrete MOSFETs have disappeared from the world, unlike the same for BJTs. So it's hard to go out and buy just a single MOSFET in a package you can put on a breadboard. Like they are out there, but like most of the time they're not anymore. Then they're increasingly being discontinued. So MOSFETs are kind of a victim of their own success at miniaturization. They've disappeared from the world in the one at a time sorts of applications. And then lastly, there's just some forbidden knowledge that, this is what, the School of ECE doesn't want you to know, but the junction field effect transistor, or JFET, is very closely related. It's a depletion type device. We'll get into what that means later. That's still used in a few low noise, high input impedance applications. So if we're going to talk about depletion type devices, we might as well talk about JFETs. What is a transconductance amplifier? Let's see how long it's going to take me to get to the answer to that. Longer than I'd like. In short, transconductance means it takes a voltage in and produces a current out. So basically, the idea is that you can put a small voltage in and get a large current out. That's the short answer. If you want a longer answer, you must wait until slide 68. Vishal. Any other questions? Transconductance, think of what conductance means. Voltage in, current out. Okay. So here is a diagram I produced of an enhancement type NMOS transistor. Let me see if I can bring up my editing tools. Oh, they don't want to work. Let's see, freehand. There we go. And of course, it replaces it automatically. So here we have ID. And that looks like a circle. Okay, this isn't going to work. If you have problems following along, do let me know. I should have tested this part of the presentation out a little earlier. But basically, we're going to say, here's an enhancement type MOSFET where we've got this P-type silicon substrate, which is the bulk. We're going to connect a metal terminal in black, and then call that metal contact the body. We're going to put a N-type well, heavily doped, so it's N plus type. You should all remember doping from the end of ECE 20001, two polarities of semiconductor. We're going to call one of them the source, the other the drain. We're going to put a oxide of silicon dioxide, thickness Tox, over this sort of channel region with length L between the two wells. And then we have this metal or polysilicon contact on top, and we'll call this contact the gate. The width into the page is W. So here we have our basic enhancement type MOSFET. To define currents, we'll say the current going down the drain is ID, and the current going up out of the source is IS. Then we'll see that it's equal to ID. The gate produces a current of 0, so there's 0 current into the gate. And then we'll have plus or minus differential voltage VGS, which is the gate to source voltage. And then we'll have VDG, which is the drain to gate voltage. Sorry, again, paranoid about questions. So if the TAs could help me, let me know when there's a question, that would be great. Now, don't blink, you might miss it. Here is the next slide, which is a enhancement type PMOS transistor, which is the exact same thing with the same labeling of terminals and the oxide and the metal contacts, except we have an N-type silicon substrate and a P plus type silicon wells beneath the source and the drain. So let's talk about an unbiased NMOS transistor. So another descriptive name for the MOSFET is the insulated gate FET, or IG-FET. So I'm going to read more from slide 18 while keeping slide 16 up on the screen. So observations about an unbiased device. The DC current that flows across the oxide or insulation layer is almost non-existent. It's going to be less than 10 to the negative 15th amps. This source body, PN junction on the left-hand side, where we body to source, you can see there's P and N between the bulk and the source well, as well as the drain body junction on the right, are kept reverse bias for normal operation. So that means that the body is assumed to have 0 effect on the other terminals. So we've gone from this 4-terminal device down to a 3-terminal device, like we said the MOSFET should be. The easiest way to keep the body out of the picture is just to tie the body terminal to the source terminal, or the most negative supply if available for an N-type MOSFET. The current is going to flow longitudinally from the drain to the source, vice versa for the PMOS transistor, with a width W comparable or many times greater than that channel length L. So this is going to extend much deeper into the page than this distance between the two wells. For the NMOS transistor, the drain is the terminal with the positive voltage with respect to the source. This is a completely symmetrical device. So how do you distinguish the drain from the source? The drain is just the one with the more positive voltage. The PMOS transistor is a complementary device with the opposite polarity doping. So we can see here that unlike the PN junction, we've got brand new device physics to study. So we're going to take a little bit of time to do this, to understand a little bit about how this works without dwelling too much on it. Again, no, I'm trusting the TAs to tell me if there's questions. All right, here is a slide we're starting. This is the field effect transistor modes of operation. So, I've got the N channel modes on the left, the P channel modes on the right. They're also called regions of operation. So we have this cutoff region, which is when the gate to source voltage is less than 0, or source to gate is less than 0 for the PMOS. So then it's cut off, which basically means no current flows through the device. If you combine that with the triode or linear region, where we have the gate to source voltage greater than the threshold, and the drain to source voltage being less than the gate to source minus some threshold voltage, you get a very good switch where you're switching between cutoff and a very linear type of switch region. We don't talk about the subthreshold mode in this class. It's more forbidden knowledge that I'm giving you. It exists. It's basically what happens when you have a gate to source voltage between 0 and the threshold. We're not going to talk about it very much, though. There's some novel uses in current research about what to do here. It behaves more like a PN junction than you might think, but it's very weird, and we won't talk about it. But the most important region of operation for us is saturation, because this is what we use to make amplifiers. So this is where the gate to source voltage is greater than the threshold, and the drain to source voltage is greater than the gate to source voltage minus some threshold. So how do we get from the cutoff mode where we've talked about having 0 gate to source voltage? Now we're going to apply some gate to source voltage here, where source is grounded, body is grounded, drain is grounded, and we're going to apply a little bit of voltage here. So we're going to get this sort of picture, and I will describe what's happening as I flip through my notes in a hurry. So reading from slide 21, when VGS is 0, there are 2 opposing series PN junctions between drain and source. Right, so the PN junctions, the diode symbols basically face towards each other, which means no current flows, which means we get a ridiculously large resistance of about 10 to the 12 ohms, way too much to let any appreciable current flow. But when we apply this VGS greater than 0 to the NMOS transistor, this potential difference causes holes to be repelled from the channel region under the gate, and it's going to attract all the free electrons from the N plus type wells. So it's going to create this depletion region with uncovered bound negative charge and create this N-type channel directly underneath the oxide layer. And then when VDS is greater than 0, the current flows from drain to source through this channel, also called the inversion layer. Why is it called the inversion layer? Because originally it was a P-type region, but now it's an N-type channel. We have inverted the polarity of doped semiconductor in this area. So NMOS transistor is also called an N-channel MOSFET. Similarly, PMOS transistor is called the P-channel MOSFET. Minimum VGS to create a sufficiently conducting channel is called the threshold voltage, V sub capital T lowercase h, also called VTN for N-channel devices or VTP for P-channel devices. So basically, we don't get this channel until VGS is greater than some level V sub capital TH. So we'll define something called the overdrive voltage, VOV, where that's going to be VGS minus VTH for the NMOS transistor. So positive charge on the NMOS gate electrode is separated from the negative charge in the oxide layer. So we can see we're going to get positive charge by this voltage source on the metal, and we've got a whole bunch of negative charge here separated by oxide. One layer positive charge, one layer negative charge separated through a dielectric. That's a parallel plate capacitor. So we've basically created a parallel plate capacitor. And thus we get a field effect where the vertical electric field, you can think of it as, arrows from the top pointing towards the bottom through that oxide, controls the amount of charge in the channel, and thus the conductance between the drain and the source. Hence the name field effect, the origin of why we called it a field effect transistor. The overdrive voltage, or effective voltage, determines the amount of charge in the completed channel. And then we're going to introduce this term, oxide capacitance per unit area, script C ox, which is defined as thus, an important parameter where it's got these certain values. I'm going to use the calligraphic C because it's a capacitance per unit area versus the normal math C, which is for normal capacitances. And then if you do your math and look at the definition of capacitance, you can see that, this is the amount of charge in the channel. Everyone with me? Someone make a sound.
Yes.
Maybe I'm giving a little bit more math, but this should be review material. Maybe with a little bit more rigorous treatment though. When we applied the small VDS, we're going to get a roughly linear operation. I'll skip through the math here. Just saying that we get, charge per unit length, and then we can solve with speed, use the Drude model from Physics 272 to get channel conductance, where we get a relationship between ID and VDS is equal to this term in the middle, where mu n is the free electron mobility measured in centimeters squared per volt second. So that's how mobile the free electrons are in response to an applied electric field. And then W over L is called an aspect ratio, where it's, W is the depth into the page and L is the length of the channel. So each term in channel conductance has a name. Process transconductance parameter, Kn prime, that's mu n times Cox in amps per volt squared, set by manufacturing process technology. So if you say, hey, we are manufacturing on a 14 nanometer process or a 5 nanometer process, you sometimes hear those terms. That means there's a certain mobility, oxide capacitance, screen area product associated with it. The MOSFET transconductance parameter uses the aspect ratio W over L, and as such is set by the MOSFET designer. And then, of course, we have the overdrive voltage. If we look back at this equation, we can see that if we have VOV as a parameter, we can keep increasing it. So it's going to look like a family of linear resistors through the origin. And that's kind of a big idea, is that, we're in the small drain to source voltage means that, we're in the linear operation. So it's going to look like a bunch of resistors, depending on the level of VOV. And then why is it called an enhancement type MOSFET? It's because there's no channel originally, and then we have to make the channel appear. So since the channel has to be induced by a non-zero VGS and it deepens for increasing VGS, it's an enhancement type MOSFET. The drain current only flows in towards and out of the source. IS is equal to ID and IG is equal to 0. So now I'm going to read to you from slide 26 while leaving slide 27 up. So what happens if we apply a big VGS when we have VGS in place to create the channel? Well, what's going to happen is the gate to drain potential is going to be smaller because there's, if you go a KVL loop, ground plus VGS minus any voltage drop in the device itself minus VGS equals 0, we see that there's less gate to drain potential here. So that means that the channel is going to be shallower here. And then as we increase VGS, this point, this part is going to get shallower and shallower, while the source side stays at the same thickness as it normally is because it stays grounded. Eventually, it's going to taper and taper until it looks like a trapezoid, and then we can do a little bit more math with, charge and drift velocity in order to get a new ID-VDS characteristic where we have this taper channel, and it's going to look like Kn prime times W over L, and then this quantity VOV minus a half VDS times VDS. So instead of looking linear, it looks like a family of summary parabolas with a VDS intercept at the origin, and then the curving, upwards, concave down, so that VDS is equal to VOV. That's what you get if you analyze this equation. So this family of summary parabolas is also a big idea. And then I'll go back to the picture on slide 25 and read from slide 27. Once VDS is greater than VOV, then the gate to drain potential is going to be less than the threshold voltage, and the channel is going to pinch off. Instead of, tapering like a trapezoid, it's going to, be like a triangle and just reach a point where it is 0 depth channel on the drain side while having a finite depth on the source side. The channel has literally pinched itself off. It's not a block channel. It doesn't prevent any charge from moving through because we have this depletion region around it, which allows the charge to accelerate through basically unimpeded. So, it doesn't, you don't get an increase in current, but you get the same amount of current once the channel pinches off. The channel is unable to change shape any further for increasing VDS. All it does is it just, moves the pinch off point back. So the current saturates at a constant value where VDS saturation is equal to the overdrive voltage for that particular VGS. So when we look here, we see that the ID no longer is a function of the drain to source voltage. It's just a function of our control voltage VGS, which is inside this overdrive voltage expression. And we get this factor of 1/2 out front. So the PMOS transistor or P-channel MOSFET works very similar to the NMOS transistor in triode mode and saturation mode, where we have these so-called square law equations. That's one name for this. The other name is Sheachman-Hodges model, but that's only if you want to impress your friends. The source must be at a higher potential than the gate to form a P-type channel. The drain must be the terminal with the negative voltage with respect to the source. Drain current is considered positive flowing out of the device, and holes carry current through the channel. So those are the 4 big differences between a PMOS transistor and the NMOS transistor. Otherwise, all these things, behave pretty much the same. So we have the channel existence condition as VGS is less than or equal to VTP. If you don't like dealing with negative numbers, because VTP is going to be a negative number, we can say absolute value of VGS is greater than the absolute value of VGP. And then we can also do something similar with lambda, which is another character we'll introduce later on that'll be negative. MOSFET transconductance parameter is now Kp, which is Kp prime times the aspect ratio, where the difference is we have mu p. So Kp is going to be lower than Kn because holes have a lower mobility than free electrons. It's hard to move a gap in the silicon lattice where charge should be than it is to move an electron that isn't constrained to move in the lattice at all. In equations, we're going to replace VGS with VSG and VDS with VSD. So the whole heart of CMOS, which is this big family of digital logic, complementary MOS, is the ability to fabricate NMOS and PMOS transistors on the same chip in very close proximity. So that's how we got this sort of digital explosion, was by having both NMOS and PMOS. So it's important to be able to work with both. So I feel like we've talked long enough about the device physics. Let's actually get into the circuit symbols. Is the depletion region neutral? Oh, that's a very good question. It is depleted of free charges. There's all these bound charges that we don't care about because they're inside the cores of the nuclei. Holes in electrons have overlapped. So yes, in an unbiased device where you're not applying any voltage across it, the depletion region will be neutral, Shenjuan. Good question. All right. Pressing on. Enough with the device physics. What does this actually look like in a circuit? So we have the 2 circuit symbols. So we have an N-channel MOSFET on the left and a P-channel MOSFET on the right. So the source terminal is always the one with the arrow and shows the direction of normal current flow. So, the current should flow down the drain out of the source. So that's the arrow on the N-channel MOSFET, and a P-channel MOSFET, current flows down the source and then into the drain. So yeah. And out. So yeah, that checks out. The N-channel MOSFET has the arrow point out of the device. whereas the P-channel MOSFET has the arrow point into the device. And usually I'm going to draw this with this little circle here on the gate of the P-channel MOSFET. That comes from digital logic uses. It doesn't really relate to what we're doing, but I will do it as something that further distinguishes N-channel MOSFETs and P-channel MOSFETs in my slides. And with these reference directions, you should not see a negative current. And then remember, MOSFETs are symmetrical devices, but the drain is always the terminal that is positive with respect to the source for NMOS transistors, vice versa for the PMOS. To summarize everything we said in all those equations and the concepts with the channel, here is a table from the Sedgwick and Smith book I used in my previous class I taught. So remember, the gate current is 0. Here's a summary of the NMOS transistor behavior. And then on slide 31, here's a summary of the PMOS transistor behavior. So hopefully, if you're want the more consolidated version of what we just discussed, this explains the key points and equations. Okay, so on slide 32, we have the first of 2 IV characteristics. So every time you are introduced to a new nonlinear device in your life, which for some of you, this may be the last time. For some of you, this may be the first of many. But if every time you're introduced to a new nonlinear device, you should ask, what is the IV characteristic? That's the first question you should really ask. It's because that really explains how nonlinear is it? Like, what's the real relationship between current and voltage? Since the gate current is always 0, that means the 2 drain current, or the 2 currents, drain current and source current, are the same. So we only have 1 current to study, and we have 2 voltages to study, VGS and VDS. Now you're asking, what about VDG? And I'm like, that would be related to VDS and VGS through KVL. So only 2 of them are really independent from each other. That's enough of that tangent. So according to this, yes, on slide 32, we are going to have the ID VDS characteristic, where we can see all of these in the triode region. We see near the origin, it looks like a family of linear resistors, like I said. And then as we increase the drain to source voltage more, we get a family of semi-parabolas that reach up to some point. And then when we have VDS equal to VGS minus VTN, we get saturation mode, where we have basically a flattening out of the ID values to a constant. There's this boundary between triode mode and saturation mode. That's a semi-parabola, and that's equal to Kn over 2 VDS squared. And I plotted it here with those values. The other IV characteristic we need is ID versus VGS. So here we choose VDS such that it's always greater than the overdrive voltage, so it stays in saturation mode. So we can see, we're in cutoff, and then up to 1 volt, we're in subthreshold mode. And then after that, it's just a shifted semi-parabola, and we're in saturation mode. Okay, I'll keep going. So for some reason, the department thinks it's very important that you know what depletion type MOSFETs are like, even though we don't really do many problems with them. I'll talk about it because, it's part of the curriculum, but I always wondered why it was part of the curriculum. So on the left, we can see an N-channel depletion type MOSFET. So a depletion type N-channel MOSFET lets a drain current flow through an implanted channel when VGS is equal to 0. So that means even when we don't apply a gate to source voltage, there's already a channel that lets current flow between the drain and the source. So as we increase VGS greater than 0, it improves the channel depth and conductivity. which is an enhancement mode. And then if we apply a negative VGS, it's going to deplete the channel and repel electrons from the channel and attract the holes from the substrate. So as you can see, it's depletion type because we start with a channel and then we can apply a voltage to remove it. We deplete the channel versus the enhancement type where we have to create the channel. So the threshold voltage is now going to be a negative number for N-channel MOSFETs. And you are able to fabricate depletion type and enhancement type devices on the same integrated circuit. So if you are wondering, yeah, you can build N-type depletion, N-type enhancement type mode, and P-type enhancement mode together. So the symbol for the depletion type shows that there's this thick bar underneath the channel, the oxide marker. So that shows that there's a channel in place under zero bias conditions. Now here's the weird thing. You could figure out and piece together what a depletion type PMOS transistor symbol would be. I didn't show it here because I can't find any of them available. They're just commercially unavailable. You can't go out and buy a depletion type PMOS transistor. So I always question, why should I make you study something that you can't buy? You might be able to, you can make one, but you can't buy it. So it comes down to your opinions on the usefulness of that. JFETs, which are these symbols here, where we have the N-channel JFET and the P-channel JFET, where there's a single bar in the symbol and then the arrow is on the gate, are always depletion type, and they can be used in many of the same situations that a depletion type MOSFET would be used. So might as well learn it because that's literally all the additional information you need to know to use a JFET. It's the same equations and everything. New message. Just to clarify, in saturation mode, ID is equal to IS. Adrian, in all modes, ID is equal to IS. Even in cutoff, when they're both equal to 0, they will both be 0. So if I go all the way back to slide 16, the only place, or I guess maybe slide 20 would be a better one. There's zero current through the gate. The body is out of the picture. So current that flows in through the drain must flow towards and out of the source because there's no other place for it to go, and current must travel in closed loops. Does that answer your question? You're welcome. So in our remaining 7 minutes, we are going to discuss procedure for MOSFET DC circuit analysis. I will probably skip forward a little bit and then come back to the examples, just because I don't think we have time to do the examples, and I don't want to do part of an example in one recording and do the remainder of the example in a subsequent recording. So here's the procedure we're going to go through. So first of all, in a MOSFET DC circuit, check to see which terminal voltages are there around the MOSFET to see if any MOSFET is cut off. It should be obvious with a little bit of training to figure out which MOSFETs are cut off. Remember, cut off for an N-channel MOSFET means the gate to source voltage is non-positive. So that would mean something weird like, if the gate is at a lower potential than the source, that MOSFET's probably going to be cut off. And for a P-channel MOSFET, you see the gate above the source voltage. That would be a clear indication that that MOSFET is cut off. So for the conducting MOSFETs, we're going to first assume operation in the saturation mode. And then step 3, perform DC analysis, using KVL, KCL tricks, starting with the large signal pi or T models for saturation mode. And you can be like, Michael, what is the large signal pi or large signal T model? We didn't really talk about those. Those are the key equations that were in the tables on slides 30 and 31. The large signal pi, large signal T, Sheachman-Hodges model, or square law equations. Those are what we're using. Step 4, compute VDS for each N-channel MOSFET and VSD for each P-channel MOSFET. If VDS is greater than the overdrive voltage for an NMOS transistor or less than the absolute value of the overdrive voltage for a PMOS transistor, then the MOSFET is indeed in saturation mode. The alternative condition is to check VDG or VGD, but I won't do that. I will be consistent and always check VDS or VSD. If for some reason, you see that VDS is less than the overdrive voltage, or, similarly for a PMOS transistor, the MOSFET is in the linear mode, not saturation mode. Your analysis is null and void and must be repeated from step 3. So then you have to go up to the previous step, make a new assumption about the state of your MOSFETs, the mode of operation, and do the steps again. Step 5, you report the results when all MOSFETs have been checked to be in the correct mode. And then step 6, which is optional, verify with a SPICE circuit simulation. So that's the way to check your results to see if you have the correct answer. So I have 2 examples queued up where the idea was we would sort of fill them out together. I will work on those offline and then prepare them for the next lecture for you to sort of write down in your notes. That's kind of how I did my class last semester. However, in the future, I think I'll move towards a different format for the future lecture slides. So the last thing to really talk about with MOSFET behavior is some graphical techniques. So say, for example, we can plot the NMOS transistor characteristics with VGS as a parameter and the KVL relationship with the supply voltage on the ID VDS plane. So say, for example, we have some sort of resistor and the drain of the MOSFET. We can figure out the equations everything must obey by plotting this dashed blue line here called the load line. Now, wherever the load line intersects with a characteristic, one of these families of curves, that is a potential operating point of the transistor where it can exist. So you figure it out and you say, okay, this dashed line has equation ID is equal to V plus minus V minus over RD plus RS minus 1 over RD plus RS times VDS. So as you can see, this first term is the y-intercept, minus 1 over RD plus RS is the slope, and then the intersection point for VGS equals to 3 is our Q point, which is our quiescent operating point, which is the DC values of VDS and ID that we should expect. So you can basically solve every single transistor in your circuit graphically. But again, nowadays, we have billions and billions of transistors, or maybe say you're making a small amplifier with 10 MOSFETs. This isn't going to be very useful when you're dealing with several data sheets and you're trying to extract all these curves and plot lines to figure out what you're doing when you have a many-stage transistor amplifier. So, we're not going to want to use the load line. So how do we choose the Q point? It's going to represent good biasing for amplifier operation. A switch would want one in cutoff and one in the deep linear mode. We're going to define the closure resistance. MOSFETs are the faster switches because they have low parasitic capacitance. That's just kind of a factoid to throw out. But the important part is the lower one. If you're choosing a bias point with an input voltage VGS and load resistance RD through a biasing network, you're going to use a voltage transfer characteristic to figure out where voltage is going to be for VGS. You want it close to the linear mode boundary where you have the most gain, but you want to have a little bit of leg room, as they say, so that the voltage can swing down without causing you to leave the linear mode. And you also want headroom to avoid clipping by going into cutoff. And then if you study biasing networks, you can get more tips on specifically where to choose the Q point. I don't plan on asking many questions about this. This is just mostly, showing you can solve things graphically. However, it's going to be better to solve, an actual biasing network like the example we're going to cover tomorrow. Any final questions? 3 new messages. Tutorials for using Spice. Yes, I do. If you're interested, I can post those and see what you're doing. I don't have the best actual here's how you do this. I usually do that with demonstrations, like how the actual buttons and layout work. But I have projects if anyone's interested in those. If no one has any more questions, I'll say class dismissed. Thank you very much for your attention today. I know this was kind of a big information dump. Hopefully we have fewer lectures like this and they're more exciting. You're welcome, everyone. Goodbye.
Hi, Michael.
Yes.
I was monitoring the Piazza, and there's a couple of students still having issues with the Zoom stuff.
We'll talk about it during office hours today.
Okay.
So yeah, we'll have our meeting in about less than 40 minutes.
Okay. Great. I will see you then.
Yep. Goodbye, everyone.